Okay, this is my second talk, and in this talk, I'd like to show you the preprocessing in displacement space. And again, this talk is sitting on the top part of this big onshore tree. And our objective is to obtain the reflection data without a ghost. And people usually measure the displacement. So it's reasonable to design a wave separation algorithm directly use the data in displacement and get its output also in that space. And then people can use this for other processing or inversion works. So here, Wagner and Secrets just provide that kind of wave separation algorithm by using the elastic data in displacement space in 1990. And this talk is just applies that algorithm on data in displacement space. And in the previous talk, Green's theorem has shown its capability to effectively separate the reference wave, specifically the ground row from the reflection data. And then it removes the ghost from your reflection data. And now, given the data in displacement space, the Green's theorem will return its capability to finish these two jobs and give you the outgoing reflection. And actually, if your only interest is to obtain the outgoing wave, and we assume that the source is above the environment surface and there is no source ghost, and actually, the Green's theorem can be arranged to remove all those other events at once. Say, you just apply the elastic Green's theorem for one time, you can effectively separate the outgoing wave from all those other direct wave, ghost, and ground row simultaneously. And we understand and aware that people sometimes use the isolated ground row for the near surface inversion, and sometimes people use the ghost to enhance the structural imaging. Like my colleague Chao will give a talk on that subject in this afternoon. And but if our interest is for the free surface and internal multiple removal, they only require that if your input data is outgoing reflection data or not. So based on this kind of interest, this approach still shows its benefit. And this alternative approach is applicable for your data both in PS space and in displacement space. And this talk will take the data in displacement space as an example to show you how to remove all those other events at once. And this is the outline here. First, I will show you the theory about this method, and then I will give you two specific examples. And after that will be the discussion and the summary. So again, this is our Earth model here. We have air and then a space of elastic world. And here we assume the property in the vicinity of the environment surface is known and homogeneous. And in this displacement world, we have our source as a force vector, has x and z components. And we have our receiver as a vector also measure the displacement into x direction and the z directions. And in this example of the talk, we just assume we only have the source in the vertical direction. And actually, you can also add your data, add your force along the x direction, because the algorithm itself doesn't need any information about the source. To say it, to apply the algorithm, you don't need to know any information about the wavelength of the source or the radiation pattern of the source. Just for simplicity, we put a vertical force here. And now we put this source on the free surface, and at the receiver side, we measure the displacement in x and z directions. Okay, now if we choose the reference medium to be a homogeneous elastic world, and its property agrees with the actual Earth along the environment surface, so at this time we will have three sources. The first source is the energy source here, and the second source is the air perturbation. And the third source is the Earth's perturbation or the Earth's heterogeneous. So S1 and S2 above the environment surface will give you the downgoing wave, including the direct wave and the ghost. And it will also give you the ground roll. And the third source below the environment surface will give you the outgoing reflection. So we are interested to obtain this outgoing reflection. So at this time, we need the green theorem. Now we put a closed surface around and do the evaluation above the environment surface inside the volume. Then do the surface integral, you can obtain the contribution from S3, or to say you can separate your outgoing reflection data from your total wave field. And this is the integral formula here, and this is another extended version of those P grad G minus G grad P formula. And let's look inside of this integral formula. Here U, as we saw, is the displacement of your total wave. It contains X and Z components. And T here is the traction along the environment surface. And it's a force vector, contains X and Z components. And use this example, or as use the environment surface as an example. We assume this is the environment surface. So the traction is actually internal force acting on the environment surface for per unit area. And this term is also required in this integral formula. So in order to obtain this term, you can either measure this or calculate this. To calculate this term, you need the information of the Earth's property in the vicinity of the environment surface, and you also need the derivative of the displacement along this environment surface. And after that, you can use this information to calculate the traction via the Hooke's law. And the third term is the Green's function, and in this homogeneous reference medium, and we can see this is a second order tensor. And the sigma zero here is the stress tensor of the Green's function. It's actually the traction along both the horizontal plane and the vertical plane. And after using these four terms and apply the integral formula, you can get your outgoing reflection data separated. It's also a displacement that contains both UX and UZ components. Okay, next I'd like to use two specific examples to show you how this method performed to help you obtain outgoing reflection data. And here we just, for both experiments, we just use one shot record, because this algorithm just works on one experiment at each time. For each shot getter, you just need to separate the wave field on its own. And the first specific example is the buried receivers, and the second example is the on-surface receivers. So let's look at the first example. Here, this is our model, and you have two-layered Earth, and the source as a vertical force acting on the free surface, and the environment surface is 100 meters below. So, and you separate, you output your separation result on the environment surface. Okay, we only look at the X component result, and this is your total wave field. And we can see this is the direct wave, and this is the relay wave. You know, this kind of interface wave will decrease exponentially along the depth. So at the receiver, when the receiver at depth 100 meters, its energy is not that significant. And this is your outgoing wave. This is the ghost or the downgoing waves. Because at this depth, so the outgoing reflection and the downgoing reflection can be distinguished in this short record. So what we are interested in is to obtain this outgoing reflection. So we need to separate these these events from all those other events. Okay, we need this, and the Green theorem can help us to obtain all these outgoing reflections. And this is the original data. This is your wave separation result. And again, to evaluate the result, we create the data with the analytical form. Because we give the model, we also have the analytical form of all these events. So we can compare this accurate result with the calculation result. Again, it's hard to see any difference. So this result is very satisfying. And the second model is everything is the same except we just locate the receiver depths on the environment surface at depth 0. So we only show you the X component result at the receiver depth 0. You can imagine the relay wave will have a very strong energy and it dominates the energy of this data. And actually, in order, you can see this clearly, it just mute some higher energy of the relay wave. But when we do the wave separation, we don't do this. We just put all this data into the formula to get the separation result. And these events are the outgoing wave and the ghost. We understand that for the measurement on the depth 0, and the outgoing wave and the downgoing wave will have the same time lags. And this is the separated S component of the outgoing wave. And again, to evaluate the result, I just create the accurate outgoing wave with the analytical form. To compare this accurate result with the wave separation result, it's again a satisfying result. Okay, now we use these two examples. We can see this approach also provides its benefit to effectively separate your outgoing reflection from your total wave for the following processing. And next, I'd like to show you about the data requirement. And from this formula, we can see in order to apply this algorithm, we need to have the displacement, and we also need to have your traction. Both terms we need their components along x and z directions. And as I mentioned, for the traction t, you can either measure it or calculate it with the Boost law. And until now, we have shown you two data sets to do the grain theorem wave separation for the prerequisites. And we can drop our conclusion here. So the elastic grain theorem can incorporate for data either in PI space or in displacement space. You can either pick either one for your own processing interest. And the second is if we are only interested in obtaining the outgoing reflection and assume your measurement surface is below the source, then elastic grain theorem can remove both the ground roll and the ghost at once. Otherwise, if you are interested in using the separated ground roll or the separated ghost for other application, the elastic grain theorem can also separate them one after another. You can back to the previous slides to have this conclusion. And the most important thing I like to repeat or re-emphasize here is we provide the method to separate and remove the ground roll and the ghost without damaging the outgoing wave. And this outgoing reflection will be used to the surface multiple and the internal multiple elimination. And this work is aiming to piece of that strategy for onshore internal multiple elimination. And we will keep you posted on this progress. And for the next step, I like to test this method on the synthetic data and the field data with near surface level variance. And I plan to deliver the code in July 2016. Again, thank you for listening, and thank our sponsor for the support and the encouragement. Thank you.